Hey there, astronomy students. This is Miss Ruark. This is Vodcast 10. We're talking about interstellar medium. All right, so interstellar medium. Let's talk about this. Interstellar medium is the stuff that is in space. There's just, like it says, a world of dust. The space between the stars isn't completely empty. It's filled with very dilute gas and dust, and it gives us some of our most beautiful objects in the sky. Okay. Interstellar medium is gas and dust that's between the stars. Okay, we do know that because we've talked about that. All right. Why are we interested in the interstellar medium? Well, because that's where clouds are born, and these dark clouds alter and absorb the light from the stars behind them, and it does a Doppler shift to the red when we're trying to look at stars. So it makes some of the stars behind them look cooler than they really are. All right, so Bare Eye Nebula. We have a nebula in the Orion constellation. One example of this interstellar gas is the Orion Nebula. Okay, so here is Orion, right? You can tell because of the three stars in the middle. All right, well, here, right there, is the Orion Nebula. Okay, it's a cluster of, I believe it's 4 stars. It's called trapezium. Yes, 4 for trapezoid, right? So 4 stars there, and that is a bare eye nebula that you can see if you look through a really good telescope at night. On a very clear night, you might actually be able to see those 4 stars separate. All right, so there are 3 kinds of nebula. The first kind of nebula is called an emission nebula. Okay, Foxfire Nebula is an example of that. See, this is the Foxfire Nebula. Looks like a fox is protruding out of there. All right. So in an emission nebula, it's hot stars that illuminate a gas cloud that's around it. Okay, it's going to excite or ionize the gas, and the electrons are going to be kicked into higher energy states. So when it excites it, the electrons are grabbing photons, and they're going up in energy level, and then they fall back down to the ground state, which produces those emission lines as they come off. I don't know why that... there we go. All right, so here's another example of an emission nebula. And another picture of an emission nebula. All right, 3 kinds of nebula. The second one is a reflection nebula. Okay, so a star will illuminate a gas or a cloud of dust that's around it. Okay, the starlight coming from the star is reflected by the dust, and that's why it's called a reflection nebula. Okay, these appear blue because blue light's scattered by larger angles. Scattered more than the red light would be. So that's why we call it an emission nebula or a reflection nebula, and it's blue. Okay, so the same phenomena, the blue light scattering more than red light because it has more energy. It's going to hit more particles. It's going to scatter than the red light, and so that's why the sky is blue. It's not because it's a reflection of the ocean. Okay, here's just another diagram of scattering. Okay, so in this diagram here, it shows you that the sunlight enters the Earth's atmosphere. Remember, sunlight is all wavelengths, all colors. The blue photons are going to hit our eyes more, making the sky look blue because these are scattered more than the longer wavelengths, and so they're all over the place, and you've got all these blue photons hitting our eyes, which make it look blue. Okay, third kind of nebula here is called a dark nebula. Here's an example of a dark nebula, the Barnard Nebula. It is a dense cloud of gas and dust that absorbs the light from the stars behind. So you can't actually see it. You see the absence of light, and that's how you know that it's there. Irregular shapes of these reveal the turbulence in the interstellar medium. I think I covered everything earlier. If I didn't, tell me in class. Okay. So these are going to appear dark in front of a brighter background, such as this Horsehead Nebula here. So there's a lighter background in the back, and it appears dark in the front because it's a bunch of dense clouds. Interstellar reddening. So this is what I was talking about when the light from stars that are distant travel through this interstellar medium, and they look red when they should actually look brighter than red. Okay, so this further evidence of this medium is called the extinction or dimming of light of distant stars and interstellar reddening. So the light from the distant stars, it's scattered by dust particles in the interstellar medium, and the blue light is scattered more than the red light. So the red light is what comes through, and those distant objects look redder than their spectral type should be. And we call that, well, reddening. Let's see, blue light strongly scattered. I think that's what I just said. Blue light scattered, so you see the red. red light can more easily penetrate the cloud, but it's still absorbed. And so if we saw invisible light here, this is what it would look like. Okay, now we can look at it through infrared vision, and we would be able to see all the stuff behind it because those things are coming through. That infrared is coming through better than the visible light would be coming through. Okay, it's not absorbed. All right. And the dust that the interstellar reddening, the dust that it's coming through, is made of carbon, silicates, irons, and ice. So interstellar absorption lines are extremely narrow. Let's see. I don't think I need to talk about that just yet. No. Okay, let's come back. Sorry. All right, so interstellar reddening, the interstellar medium will absorb that light more strongly at shorter wavelengths. So at these shorter wavelengths here, it's absorbing it more. Okay, as you get higher and higher as these wavelengths get shorter and shorter, these UV wavelengths, it's going to absorb it more and more. So you're not going to be able to see it as much. That's why we could see in that last picture here, we can see all this stuff back here because this is infrared. It's got a longer wavelength, so it's going to be able to pass through those clouds much easier. Okay. All right, interstellar absorption lines. So these are extremely narrow for interstellar medium. Interstellar gas is cold. See, so here's the absorption lines, very small and thin. And they're, well, I'll get to that in just a second. All right, so interstellar gas is cold and has a very low density, makes the interstellar lines much narrower than the spectral lines produced in stars. Multiple interstellar lines reveal that the light has passed through more than one interstellar cloud on its way to Earth. All right, so these can be distinguished from absorption from the wrong ionization states. So in this one right here, it should not have calcium ions in it. And how do we know it's calcium ions? Because it has more to it than just what's shown here. But these lines here are from calcium ions, and we shouldn't have those calcium ions if it's in a certain type of gas. And so they know by looking at it, hey, this is the wrong ionization states. We shouldn't have those. All right, well, we can also tell if it's, we can tell because the small line is too small. It's not wide enough, which means it has too low of a temperature and too low of a density. Okay, so here, this would be a broad stellar line, okay, and these would be extremely small and narrow interstellar lines. So that's how we can tell this interstellar gas. Okay, and then see if we have multiple components. So several clouds of interstellar medium with different radial velocities. All right, so the structure of the interstellar medium, it occurs in two main types of clouds. You have the HI clouds or the H1 clouds. These are colder clouds that have neutral hydrogen in them. They have a moderate density, and their size is about 100 parsecs. And then you also have your hot intercloud medium. Now these are hot. They have ionized hydrogen in them because they are hot. The atoms are excited. And you have a low density. When it's hot, the gas molecules expand and the density gets lower. And the gas can remain ionized because it has a low density. All right, so how can we observe the interstellar matter or interstellar medium? All right, so we can observe this using, we can observe neutral hydrogen using the 21 centimeter radio line. Okay, so electrons in the ground state have slightly different energies depending on their spin orientation. We'll just kind of cover this real quickly, but I'm not going to go too far into it. So here you have this proton is spinning, and when it's spinning this way, the electron is going in the opposite. It's spinning, but it's spinning in the same direction. The electron's traveling down and around, going clockwise. Okay, if the electron or the proton is spinning in the same direction, but the electron is spinning opposite to it, then it's going to go counterclockwise. Okay, so that's what it's talking about, spin orientation, magnetic field due to the proton spin. Okay, all right, opposite magnetic fields attract, lower energy. Equal magnetic fields repel, higher energy. Okay, what does that mean? Well, that just means if they are spinning the same way, it's going to spin around clockwise, it'll be a lower energy. If it's spinning opposite, it goes counterclockwise. Okay. Transitions from higher energy to lower energy spin state produce a characteristic 21 centimeter radio emission line. All right, so radio emission line is just this 21 centimeter radio emission line. Okay, And on this, it tells you that this is where you can see your neutral hydrogen. Whoops, go back. Let's see. Radio observations at a wavelength of 21 centimeters reveal multiple clouds of neutral hydrogen, and these clouds drift through a warmer but lower density intercloud medium. These radio telescopes that are tuned to other wavelengths had detected of nearly 100 different molecules in the interstellar medium, but most of them are found in giant molecular clouds. All right, so these molecules that can be found in the in these giant molecular clouds, okay, these molecules store specific energies also depending on how they rotate. They also store specific energy depending on how they vibrate, okay. And the transitions between the rotational or vibrational energy levels leads to this emission, which is typically going to be given to at radio wavelengths. But, however, the molecules that we can see most readily in space, two of them, carbon monoxide and hydroxyl, are both can be seen with radio emissions. And then the most common one in space is the H2, or hydrogen gas, or molecular hydrogen, and it can't be seen unless it's with ultraviolet absorption and emissions. It's difficult to observe. But if you see H2, or hydrogen gas, there's also going to be carbon monoxide to go along with it. So they use the carbon monoxide as a tracer for hydrogen gas in the interstellar medium. Okay. Let's see, what else? Infrared observations made from orbit have detected dust in the interstellar medium in the form of the infrared cirrus clouds. And they call them infrared cirrus clouds because they look like cirrus clouds. X-ray and far ultraviolet observations have detected very hot coronal gas produced by supernova explosions. So we'll talk about coronal gas here in just a second. There are 4 components of the interstellar medium. Okay, so here are your 4 components. You have the HI clouds, the intercloud medium, which is H2, coronal gas, and molecular clouds. So let's talk about these. Molecular clouds, this is where the molecules are easily destroyed by ultraviolet photons from hot stars. They only survive within dense, dusty clouds where the radiation is completely absorbed and it can't penetrate the molecules. Okay, so these are called molecular clouds. All right, and in these molecular clouds, here is your ultraviolet radiation is coming in, and it can't make it all the way through to this little spot here. It keeps getting bounced out and absorbed and changed into lower energy. So the UV emissions from nearby stars destroy molecules in the outer part of the cloud where it's absorbed, but it doesn't destroy what's on the inside. The molecule survives there. Okay, and on the inside, it's cold, dense, molecular part of the cloud. The largest molecular clouds are called giant molecular clouds, and they have a diameter of 15 to 60 parsecs across. The temperature is about 10 Kelvin, which is pretty cool if you think about it. Not cool, but cool as in cold. And their total mass is about 100 to 1 million solar masses. So it's pretty massive. All right, so your interstellar dust. Probably formed in the atmosphere of cool stars, mostly observed through infrared emissions. Okay, here is a infrared picture or image of a cirrus interstellar dust cloud. Okay, and these IR and radio emissions from molecules and dust are efficiently cooling gas in the molecular clouds. All right, coronal gas. This is a very hot, low-density gas in the interstellar medium. Temperature is extremely hot. It has small amount of particles, so it's really light, low density, and it's observable in X-rays. So this is a Chandra X-ray image of the Cygnus region. It's called coronal gas because its properties similar to the solar corona, but they're completely different in origin. And they think that it originates in supernova explosions and winds from hot stars. Our sun is actually located within the edge of a coronal gas bubble. Ooh, pretty cool, huh? All right, interstellar cycle, almost done. Stars, gas, and dust are in constant interaction with each other. So hot stars ionize gas, producing H2 regions. Okay, those H2 regions, the young star clusters illuminate the remnants of their mother clouds, producing reflection nebulae. All right, and then from there, young star clusters leave trails of rarefied interstellar medium behind. From there, we got supernovae of massive stars that produce coronal gas and enrich the interstellar medium with heavier metals. And then from there, it goes to the supernovae trivers shock waves that send in the interstellar medium that lead to the compression of dense clouds and new star formation. All right. And then that turns around and stars are formed from dense molecular cloud cores, which then goes to hot stars. And that's it. See you in class.